Hello everyone, we're glad to introduce our project to you. So our project is optimizing the performance of biomimic cellular structure under the blast loads. And these are our team members and our supervisor. Basically, in this project, we are trying to analyze the performance of biomimic cellular structure under the blast loads. And then we need to find out a certain cellular structure with the best blast energy absorption capabilities. So firstly, we need to identify the cellular structure type. And in this stage, we mainly refer to the previous papers. And then we constantly test the performance with different parameters. Find out which parameter will provide our structure with the best performance under the blast loading. Of course, we also use the 3D printing modeling technology to verify our simulation result. So the background of this project is nowadays the natural and man-made hazards such as the blast have claimed millions of lives and caused significant damage to structures. For example, in 1995, the Oklahoma bomb attacks destroyed more than 300 buildings and killing more than 150 deaths. And because of the lightweight and the superior energy absorption capability, the cellular structure are at the forefront of innovative research for extreme loading application.
As you can see in the picture which is on the top, these are the 5 models we create. By comparing these 5 models in terms of their peak reaction force and energy dissipation, we find that the bio-inspired structure, which is the 4th one, has a relatively low peak reaction force and high energy dissipation. This is exactly the performance we want. So let's go to the picture below. We modify alpha and the beta angle to further improve the performance of our bio-inspired structure. Finally, we find that when alpha is 25 degrees, beta is 45 degrees, bio-inspired structure has the best performance. As you can see in the table, it has the lowest peak initial reaction force among these models and the highest energy dissipation. Although the mass is slightly higher than the original one, it's within an acceptable range.
For the innovation of the project, there are 2 key points. Firstly, it is a bio-inspired structure. By observing the structures of porcupine quills and trabecular bone, we can see that there are concave cells and convex cells in both 2 structures. So we combine this design in our project and do further analysis. Another point is that it is different from the traditional structures like hexagonal structure and reentrant structure. For the traditional structures, you can see that the cell angles are fixed, so it means that it is difficult to improve the engineering performance. While for the bio-inspired structure, several parameters can be changed. For example, the alpha angle, the beta angle, and the thickness of the unit cell. So different mechanisms can be observed. We can adjust the several parameters to achieve a new design which has a better engineering performance.
There might be some questions about our project. The first question, how is the explosion load assumed in different directions in the experiment? Since we have a 2D model, the acting surface of the explosion load is limited to the upper and the lower planes of the structure. So in an ideal situation, we assume that the explosion load is generated only in the vertical direction and will not have an out-of-plane effect on the structure. The second question, how to transfer the 2D model to a 3D situation. To simulate the 3D case, we have generated a benchmark 3D structure. This is our unit 3D reentry cell. And then we can assemble the structure like the figure below. And then we can use OPCUS. The same methodology can be used to find the best 3D structure, while the specific details need further investigation.